Welcome to today's webinar, where we have special guest Marcus Bever presenting on the NASA EagleSat project at Embry-Riddle Aeronautical University. My name is Katie, Communications Manager here at Vitech, and I will be your host during today's presentation. Although CORE is primarily a commercial product, Vitech is proud to provide licenses through a grant program to qualified institutions for educational purposes. The EagleSat project is the first undergraduate research project to qualify for this program, and we are excited to share with you about the project, the students who have put in the efforts, and what impacts CORE has had on the process. Our guest today is Marcus Bever. Marcus is currently pursuing his Bachelor of Science degree in Aerospace Engineering at Embry-Riddle Aeronautical University in Prescott, Arizona. He is serving as the systems engineer on the school's CubeSat development program, and he's been doing that for 2.5 years, and he enjoys working on the successful integration of the satellite, which he hopes will soon mark the university's first CubeSat to orbit the Earth. While not working on homework or projects, Marcus likes to spend his time running or researching aerospike rocket engines. Before Marcus gets started, I have just a few housekeeping items. We will be answering questions today at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Marcus will answer as many questions as he can today, but if we don't get to your question, we will reach out to you after the webinar. The webinar is being recorded today, so if you experience connection problems during the live presentation, a recording will be available by request within 24 hours of the live version. The recording will be published to Vitech's webinar archive located on our website. I will send the link out to that in the chat window. I'm now going to turn the presentation over to Marcus. Welcome, and thank you for joining us.
Okay, thank you very much, Katie. So yeah, this is the first webinar that Embry-Riddle has done with Vitech, and we're very pleased to be here. Today I'll be going over the implementation of systems engineering within our CubeSat development program here on campus. Okay, so to start off, I'll explain a little bit about the EagleSat program, who we are and what we do. I'll then be going into more of the technical details about the engineering of our satellite and how we've been able to capture the complexities of that, along with requirement updates, traceability, and information flow between teams, and how we've been able to address that using Vitech's core program. Following that, I'll be going backwards in time a little bit to when we started the process of implementing systems engineering within the EagleSat program, and my process of learning that way of thinking. I'll then be moving on to the iterations of development following that to what has brought us to our current status today. I'll be wrapping up with some time for questions, and so yeah, well, let's get started. So the EagleSat program was basically launched in 2012 with our submission of a proposal to NASA. It's part of the NASA CubeSat launch initiative, and as such, NASA will take care of the launch aspect, both identification of the launch and paying for it. It's funded through another NASA program, the Arizona NASA Space Grant. And so they sponsor interns and scholarships for students to work on this project. It's also funded through Embry-Riddle Aeronautical University, and we have many sponsors that make the product possible, such as Vitech, Advanced Circuits, and Wood & Douglas. The primary purpose of our mission, or the primary purpose of the program is to educate students and to facilitate the engineering education that they're receiving as part of their classes. With this specific satellite, we're hoping to detect bit slips in computer memory and study how that is impacted by solar radiation. We will also be looking at the orbital decay of the satellite over time to try to develop a more accurate model of what happens to CubeSats once they're launched. Looking at the different subsystems that comprise EagleSat, and granted, this is EagleSat 1. We are hoping to launch multiple CubeSats in the years to come. We have 6 subsystems. The structure and onboard computer were purchased independently so that we could continue development of the more complex systems. However, the onboard computer does still require a significant amount of programming. We also have our electrical power system responsible for collecting power, storing it through supercapacitors in place of batteries, and then distributing that to the rest of the boards. We have our communication subsystem responsible for interfacing with the ground station in particular and managing the relationship or managing the data flow between the onboard computer and the ground station software. Our GPS board is focused on looking at the orbital decay study performing the orbital decay study of the satellite over time. We also have a computer memory experiment. Last but certainly not least, it's one of the most complex systems on board our satellite. So 2 years ago, this was our team. It has since grown to 39 students and 4 particularly dedicated faculty members that have served to mentor the students and to support the program. Those 4 faculty mentors consist of the Dean of the College of Engineering here at Embry-Riddle, the Associate Director of the Arizona NASA Space Grant here at Embry-Riddle as well, the Department Chair for Electrical Engineering, and the President of the Arizona Near Space Research Group. They do a lot of balloon flights and have provided a testing platform for student payloads in the past. So hopefully that gave you a good overview of where we come from. I'll now be looking into how we've been able to implement core to capture a lot of the design challenges that this project presents. So we're building a 10 by 10 by 10 centimeter cube for a satellite, and I'm continually amazed at how complex the system can get. So the primary systems engineering responsibilities, of course, consist of requirement management of the project, then addressing subsystem interfaces and risk management as well. Over the past semester, we've really seen a transition from the requirement management aspect to looking at more interfaces and risk management as the development progresses. The primary systems engineering responsibilities, again, are requirements management, and that we're seeing less of now that the program has matured, although there's a caveat with that, so I'll return to that in a few slides. And we have managing the subsystem interfaces and making sure that subsystems can integrate effectively together, and then also addressing risk management. On the right side, you can see a CAD drawing of our satellite from the structure and onboard computer files provided to us by Pumpkin, who we bought them from. Previously, especially, the teams, the subsystems, were looking at a lot of design trade-offs to try to find the optimal solution to a lot of their problems in order to meet the requirements and the functions that they were expected to perform, or their subsystems were expected to perform. So we saw a lot of that, especially in the PDR phase. Currently now, we're looking more at verification and validation of those requirements through testing. So we have testing procedure development outlines, and we're moving toward that in that direction as we approach CDR. Before I get to the last bullet point too, so this project originates from 3 primary requirement documents. On the far left in the corner, you can see just a snapshot of the Embry-Riddle CubeSat proposal to NASA that was submitted in the end of 2012. We also have in the center our interface document with the orbital deployer. So that allows us to properly interface with the mechanism used to launch the CubeSat from the rocket itself. And then, of course, we have the program overarching requirements given to us by NASA as part of the Launch Services Program. 2 of those documents also have revision statements on them. And it's not showing, that's okay. So it's been a challenge in order to capture all of these requirements effectively and make sure that none of them get left out or forgotten. There's a revision statements. And that's really where the power of core comes into play. And on top of this all, too, this program is really run by students. And so it's important to take into account that we have limited skill sets sometimes, and our schedules are such that our priority is classes. And so that adds just complexity onto the aspect of communication and really making sure that that informational flow is there. And so that impacts a lot of our how we conduct the program, and also the value that we get from using core. This satellite too, because it's so small, we're limited on weight and power, and so each design decision that a subsystem makes most definitely impacts everyone else. And so it's that coordination aspect is critical to making sure that this is a successful mission. So taking that previous slide in mind, we now have core, in which we've been able to address or identify 16 risks and concerns. 15 of those just came from a single meeting where all subsystems were requested to brainstorm possible concerns and risks associated with their subsystems. And so it's our goal to make sure that each of those identified risks and concerns it's assigned to I guess you could say an organization class within core, but ultimately that subsystems, those teams take responsibility for addressing those risks, and then if we are able to extend the traceability to design elements as well, that should facilitate that process much more. And so that's an active area of work at the moment. And we also have 17 verification requirements to help with the verification validation process. And so those are traceable to the originating documents I mentioned in the previous slide. And again, as subsystems develop tests, or as the teams develop their testing procedures, those play a key role, and that's an area we would like to expand as well. Core also provides a great unified solution to document design decisions and the rationales behind choices that were made. And that's been really helpful because we were able to capture so many of the details within one program. So requirement updates. Now, as a university project, not everything goes to plan all the time. And so it's important that we're flexible, and it's about how we address that needed changes at times when we might not like to at first. When we started the program in, well, I guess back in 2012 or 2013, we were originally planned to be launched by the California Polytechnic University, their PolyPicoSat Orbital Deployer, or PPOD. That's just a system they use to launch their satellites. Since then, however, our mission changed a little bit in that we were hoping to instead be launched from the International Space Station as opposed to being jettisoned from the rocket itself. And so that put us on a different requirements track for the NanoRacks document that I mentioned previously. And again, just the interface. We'd actually be launched from the Canadarm if that was the case. However, due to the rocket explosion last October, we may be switching back to the original requirement document from Cal Poly, the PPOD interface document. And we have a much different orbit now. So that's resulted in some design challenges, I guess, in how to implement that new orbit within our design and how that impacts different subsystems. Instead of about a 52-degree orbit, we're now looking at a retrograde orbit of 100 degrees, roughly. And so that really impacts the orbital mechanics and the power behind a lot of that. But yeah, at the moment, we're still on the CubeSat, or the NanoRacks CubeSat deployer document, and that's still the active document within the core database. Once we made that change from 2013 to 2014, we were able to scale back on a couple of requirements, and that was very advantageous to us because it allowed us to streamline the verification and validation process that we're going through now. Some of that was just reworking them so they're more generalized and apply to multiple areas, but also it helped that the NanoRacks document is a little bit more concise than the Cal Poly document. So currently we have 100 originating requirements exactly. A nice round number, I guess. All of this really begs a question about how do we properly go about communicating these changes and analyzing the impact that some of these updates have on the project and on specific subsystems. And so, and that really ties into the traceability aspect within core. And traceability is huge within systems engineering, and I'm not really doing it justice by just spending a few slides on it. So you'll hear me refer to it throughout the presentation. But within core, and especially within our project, there's an emphasis on developing traceability across different classes. So for example, how a requirement will impact a function, or how that function will impact a piece of hardware, and how that hardware is documented, and what risks that generates, and so on. And so that really allows us to not only see how things are impacted during an update, for example, but it also gives a very comprehensive contextual background for any specific element. So we can say, for example, we need this antenna placed in this configuration because we're limited on the length of protruding surfaces in a certain area. We also have to perform these functions. And so this has been a design trade-off, I guess, between multiple configurations, and this was the optimal one. So we're able to really record all of that within core. There's a capturing of interrelationships, too, between different elements, between classes. And that really helped us to ensure that we were building a consistent and complete design that doesn't have any contradictions within it, avoiding those conflict areas through a much better understanding. So it allows us to break things apart in that way and just really analyze it independently, analyze it, the individual elements independently, with their context noted. The implied need for that, of course, is lots of communication, which is a challenge for sure, but it's one we are addressing. Core has been an invaluable tool to achieve that. Also, there's just the justification of certain decisions that have been made and how that's been captured within those interrelationships. So, for example, derived requirements that for the board configuration, why it needed to be like that, and what the reasonings were behind that. But enough of words. Let's get to some examples. So this is a requirement traceability hierarchy that looks at a launch requirements, and specifically the power-up delays associated with the launch of our satellite. So you can see here we have underneath the main parent requirement here, we have 3 different child requirements. The first is the launch power activity, in that we are not allowed to power on our satellite during the launch operation. After launch, we are delayed. We're not allowed to power on major components until 30 minutes. And then we have a transmission delay of 45 minutes that supersedes that. You can see here that a lot of different, you can see here, I guess, the decomposition of requirements and also the functions that are spawned because of that. So, for example, the fact that we're not allowed to launch, or we're not allowed to power on during launch, means that we have to have certain real-time clock circuit isolation things, and we have to operate at certain frequencies. We can only draw certain current for our real-time clock. And it's also part of the overarching function of undertaking that launch day. So moving forward, we have another requirements diagram. This one covers several different classes. At the very top, we have a derived requirement of that board stack configuration I mentioned earlier. And then you can see within here the derived requirements that explain why that requirement is in place, the parent requirement. And so we have our explanations there. And then we also have the function on the far left that we have to perform, and the associated pieces of hardware that are assigned to meet these requirements. And so these diagrams are especially helpful for us in communicating the details across subsystems, making sure that none of those details are lost, and that also too that we're consistent in how we document things and represent these decisions. There's also aspects of document traceability. Most of the originating requirement documents I mentioned earlier cover tens of 40 or more requirements, but this one is a unique one in that the communication band plan for radio transmissions is fairly concise. And so this is a great example of how we've been able to take that document, figure out exactly which requirements it impacts, and then you can see exactly what elements that requirement in turn impacts. So for example, the process of sending data through the antennas, and also the hardware for our transceiver and our ground station hardware. That's all tied to the requirement of maintaining communications in the ultra-high frequency communication band, which is documented by the ARRL band plan. And so if we had to change that top band plan, we could immediately see which aspects of our program are impacted by that, and how best to coordinate their updates and make sure that we accommodate all changes. You can see here we have a physical hierarchy that was generated, and it's very similar to that color wheel I showed earlier. And so, again, it's all about context. We have our satellite up top, and then you can clearly see the different subsystems that comprise that satellite and some of the distinguishing components that make up the subsystems. And so it's just another way to communicate as best as we can these details and make sure that, as much information is communicated as it can be communicated as possible. So, all of this really begs the question: how does one fully communicate an understanding? And this is something I've thought about a lot in my role as a systems engineer. Is, you know, I might have an understanding of a subsystem or context in which the design decision was made, but unless I can really communicate that to the, you know, subsystems involved, it doesn't do much good. And so, you know, it's been this program has been a great exercise, I guess, in really exploring the different ways in which to do that. And of course, you know, meetings are invaluable. There's nothing that really can replace face-to-face interaction. But Core has a great, some great tools that can help facilitate those meetings and help facilitate the understanding that is imparted during that. One of my favorite is actually the system description documents that are automatically generated from the elements within Core. I found this to provide a very detailed view of the subsystem, while remaining concise enough that is not too overwhelming. You know, within a system description document, you have a list of all the functions and requirements that a subsystem is expected to satisfy, and also the expected hardware they're currently using. And so, if they have any changes, then they can make sure that that gets fully communicated. At the very end of those system description documents, it's also possible to include a requirement traceability matrix. And that's great because it gives a quick snapshot about how everything fits together, which is very powerful and very useful in discussing the system and discussing how everything operates. Something that I've used to support the system description documents is just exporting a basic table of all the requirements within Core. So for currently, I think it's at 9 pages, and you know it's not organized except for just by number. But the purpose of this is kind of to provide an index for people to reference. And so within the system description document, it'd be possible to you know, identify the requirements, look up, you know, note the number, I guess, and then if that description isn't fully presented in that SDD, you can then go to the index and look it up, or if you have any other questions about what a number would pertain to. It's a great way for systems to have that resource, I guess. So one thing I'm a huge fan of is diagram development. I mentioned several hierarchies previously, and that's been very, very helpful for presenting a context. We also have functional flow block diagrams that can represent sequencing of operations. And you know, I found that sometimes it's easier for people to look at the functional flow block diagrams and understand the system, since you know, a lot of people are used to thinking in terms of the sequences of operations. So there's one more hierarchy I wanted to show you before I move on to the FFBDs. And this is just a functional hierarchy of our ground station operations. You'll notice that in front of each number there's an FS, just designating a supporting function. So FS.1, FS.1.1, and so on. And so, you know, it outlines all the elements of the parent function of supporting the satellite, you know, as the primary purpose of the ground station. But if we take those last 4 elements, it's very helpful to look at those in an FFBD, because you can then see how they interact with each other. For example, the software has, you know, 3 primary functions, or 3 primary threads of functions, if you will, in that it has to track the satellite, it has to interface with the satellite, and it has to interface with the end user as well, who's either receiving data from the satellite or might be sending data to the satellite as well. You know, you can then see that the ground station downlink request has to interact with the with receiving the downlink as well. And so there's you know, on a very basic level here it's presented, but you know, you can extend this into far more complex areas as well. This particular diagram, or section of a diagram more accurately, the entire diagram outlines standard operations of the satellite for any standard day, I guess, and so it's very comprehensive. But this particular diagram was actually developed during a meeting, and so one of the great things about Core, I guess, was that we could just put it up on the screen, and then as people discussed, we were able to fill it in. And so it allowed a lot of, it allowed capturing a lot of the ideas that were presented at a meeting within a diagram actively during that process. And so in so doing, the subsystems were able to, or the team leads, I guess, were able to really understand how, not only how the process worked, but also how the satellite was expected to operate and how their operations fit into the global context of satellite operations that were expected. And so you can see here we have an if sufficient power indicator on the left side because, again, we are a very small satellite. We are limited on the power available. And then we can start with a GPS operation up at the top, and then we'll collect GPS data for a time, and then we'll power off the GPS again to save power. The comms board, we'll power on the comms board, and then we'll either go into a beaconing mode or receiving mode if we're receiving an uplink, or if we're looking for an uplink to receive from the ground station, or finally, the last operational mode would be active communication with the ground station back and forth. And we'll loop that process as much as is needed throughout the standard day. And so that kind of captures our use of the functional flow block diagrams within core. So now I'm going to backtrack a little bit into when we decided to implement core implement systems engineering and core as a decision thereof within the program. And so, when I came to Embry-Riddle, I was able to get involved with the EagleSat program just as the proposal was being submitted to NASA, so I got to help edit that. But we really didn't have a plan for how to put everything together. We had an idea of what we wanted to do, the decay study and computer memory analysis for bit flips, but we didn't really have a set idea of how we wanted to manage that and make sure that everything integrated together in a succinct and coherent way. Initially, I was just a brief liaison between teams, but we realized that we really needed more of a structured methodology to address this. And so, thankfully, Dr. Gary Yale, who's actually in the room with me at the moment, he was able to start kind of a mentoring program for students and spent many hours mentoring both myself and another student on the process of systems engineering, which at the time I had no idea what it was. So that one-on-one training, he provided tutorials of using core and how to properly address that, and many suggestions and examples of work. So that training, I guess, really helped me to understand not only the process of systems engineering, but also the power of implementing it within our engineering program. And you can see on the right there's a diagram that outlining the different aspects of traceability and the vocabulary associated therewith. And it's been neat because as Dr. Yale passed that knowledge on to me, I've been able to work with that knowledge over the 2.5 years that I've been involved with the program and really get a feel for systems engineering. And I'm at the point now where I'm starting to mentor 2 additional students in the systems engineering effort for the CubeSat program. And initially too, as I was learning the ropes of it, learning vocabulary and what traceability was and how to connect everything together, core also served as a great guide to the systems engineering process. And then if I didn't quite understand something, I could either look into documentation or I could just play around with the different aspects of traceability that could be established. And so that was really helpful, and it still is now as I continue to learn what systems engineering is and how best to implement that. So it's a very very powerful tool, not only in its capability but also as a resource for learning for students. And so I'm very thankful to have been able to work with it over the years. So from that initial decision to use systems engineering and from Dr. Yale's familiarity with core and our decision to implement that within the program. And also, I should mention too, Vitech's willingness to sponsor that. So thank you very much, you guys. From there, as a school project, we went through many iterations of design. Initially, right, we started with importing requirements into the database, the originating requirements, and making sure that we captured accurately all those that were addressed within the originating requirement documents. And then from there, establishing traceability between those so that we no longer had 3 isolated documents, but rather we had 3 integrated sets of requirements, so that we were able to really get a better idea of the scope of this project and what it would take to make sure that everything was addressed. then, from there, there's the recursive process of deriving more elements, deriving requirements or functions, filling in the physical components that would make up the system, or even the software aspects, I suppose, to some extent. And so there's that iterative process that was continued. Then we had the originating requirement change back in 2014, and so we were able to implement more of a, we were able to use some of the knowledge we had gained from our first iteration of requirements within core, and really capitalize on some systems engineering experience and streamline those requirements, make them more accessible to subsystems and more applicable. Also too, because we're a university, right, students come and they graduate, and so we've had cases in the past where a student will they'll be exceptional in a certain area, but then they'll graduate and they won't have had the chance to pass that knowledge on to a mentee, and so we've had to rework the mission in some cases, or perhaps not the mission, but rework certain subsystems to accommodate the students who are involved with the project. And it's just another challenge, but it most definitely keeps things interesting. We've also recently, especially, but we had to change in hardware suppliers for solar panels, and we were no longer the solar panels we were originally planning to use no longer produced those, and so we were able to find similar ones, but there's nothing is exact, I guess, and so we've had to just analyze how they would impact the design, how they would possibly impact the mission, and then make sure that everything gets addressed, and so that we can still fulfill all the necessary functions and satisfy all needed requirements through this new hardware. And then, of course, as I mentioned, we changed our satellite orbits by quite a bit, from 52 degrees to a little under 100 degrees, so a regular orbit to a retrograde orbit. And so just analyzing the design impact of orbital mechanics and power, and that's been a large one, but it's been a great experience, I guess, to take all these elements and really just work with them as best we can with the resources we can. So currently then, we were originally going to have our CDR, Critical Design Review, this semester. However, because of a lot of those changes in the past few weeks, we decided to go and push that off by one more semester. We are hoping to launch in November of 2016, so we do have some time in there. But it would be nice to get the CDR out of the way, I guess, and to reach that milestone in our engineering development. At the moment, then, in order to meet that, we are working a lot on testing procedure development and testing the satellite at the subsystem level, and even at the component level within the subsystems. And so, you saw that picture earlier in the presentation of our board stack. So that was one of the first times we really had the chance to integrate everything, to integrate several subsystems together and see how they interfaced with each other, and making sure that all kinks worked out. And so that consisted of 5 out of 6 boards, or 5 out of 6 boards that we're hoping to fly. Also, as another NASA Space Grant program, there's a High Altitude Human Payload Project, or HASP. And so we've been using that in the past as a testing platform to test different aspects of our satellite. And so this coming fall, we were hoping to test the most updated engineering model of our satellite on that HASP program, in order to get the most realistic testing environment, in order to get the most realistic testing environment possible. Figure out and identify early on, any potential risks once everything has been integrated together, and how we can go from there to make sure that we are, developing a very coherent system that is robust and redundant in the areas where it's necessary, and it will ultimately fulfill all of our mission goals. Again, we were looking at the possibility of shifting into the PPOD requirements, which will mean rebuilding some of that core database. But with with that aspect of traceability, we won't necessarily have to throw everything out, but we should be able to keep a substantial amount of the work that's already been done. One thing we're currently working towards as well is expanding the traceability into derived aspects of the derived elements, I guess. And so that there's really that relevant traceability as hardware design progresses and as requirements get built. I mean, that's really important to the systems engineering effort, so that subsystems can utilize a lot of that so they're able to utilize the results of spending so much time on engineering the system within core. And so our future goals then, the top priority for us is to freeze these requirements. We've gone through a lot of changes in the past, and so if we could get these requirements frozen and set in place, it'll make it a lot easier on the teams themselves in order to build testing procedures towards those requirements, in order to verify that they're meeting the requirements and designing to the right ones. So that's the top priority. We would also like to develop a system of configuration control for documents. Not only the requirement documents and documents that Core will generate automatically, system description documents or requirement matrices, but also things like testing procedures, the hardware specifications, that we have a unified database, exactly what is applicable to our subsystem, what is applicable to our satellite, to make sure that we don't have subsystems or teams working off old specifications, but rather we're designing to the most recent and most current and applicable documents available, and documents that we've generated as well. One of the things, one of our known areas that we need to work on is figuring out how to address software requirements, and how to properly capture those within core and word them appropriately, and also how to develop testing procedures for them. Software is can be a little ambiguous, I guess, compared to hardware. At least for me, it is, with my limited experience. And so, one thing I would really like to do is to meet with professors, especially in the software engineering department, and really learn how to on their side, how they like to see requirements written, and then how to take that and to implement that as part of the engineering or systems engineering effort within the CubeSat project. I mentioned the verification requirement class within core, and so we would like to expand a lot of the elements within there to address or to allow for the linking of testing procedures as part of that. And as testing procedures are developed and as they're updated and as they're ultimately signed off that yes, this test was completed, it would be great to to understand very quickly the immediate impact of that and which requirements have been verified, which requirements remain to be verified and remain to be tested to ensure proper operation of the satellite, ultimately validated against their originating requirement documents and mission concept. I mentioned earlier as well that I'm working to mentor 2 new students in the systems engineering effort, and so we would really like to see the launch of a systems engineering team that would be able to address a lot of these complex challenges that we're facing. If you remember earlier, I mentioned that we're managing requirements, we're managing risks, we're looking at interfaces, and so it's a lot to manage, most definitely. And so I think that could be most effectively worked on as part of a highly integrated systems engineering team. Obviously, communication would be an integral part of that, and so we would like to work towards that. So yeah, in conclusion, I've given you guys an overview of the EagleSat project as a whole, what we do, and the missions that we're hoping to accomplish, both scientific and programmatic. I've looked at the engineering effort and the associated challenges. We're a small satellite, but we still have a very a relatively large number of elements within that, and it's a challenge to coordinate all of that, to manage the risks within that, to look at how updates are carried through within the project, and aspects of traceability, of course. That really is huge, because traceability is what pulls everything together. I mean, what really makes a satellite integrated is, being able to say that, this piece of hardware is there because we need to fulfill this function, or because we're specified by this requirement. And so the traceability is, it's a top priority for the systems engineering team, as I mentioned. Again, facilitating communication, and not just through meetings, but also through being prepared for those meetings, through documentation. A large amount of which is produced through the core program, and it's very capable and very powerful in that. So it's been a very huge asset to the satellite development program. I also went through some examples of systems engineering, the diagrams that we've been using in order to again, achieve that communication. It's a means to achieve communication. It's those hierarchies and functional flow block diagrams. I also looked at how we've implemented core, from learning the basics of the programming, the basics of systems engineering, and how, as our hardware design progressed, I've been able to refine the database, the core database of requirements, and really look at the best ways to implement that. There's always lessons learned. And so that's been an ongoing process, and a very positive one too. I looked at the current status of the project as well, and where we are currently, approaching CDR, and last but not least, I looked at our future goals, where we'd like to go from here. We would like to launch multiple CubeSats as well, and so systems engineering will definitely play a large role within that. So with that, I would like to thank Vitech very much for the support of this project. It's been core has definitely been an integral part of the development of EagleSat, as the name would suggest. I'd also like to thank Dr. Yale for his willingness to mentor the student systems engineers, for his dedication to the program from day one, really, and how he's really supported us in every way possible. And also to the rest of the Embry-Riddle EagleSat team for making it all happen. It's one thing to design it on paper, but to implement it and go through the process of refining it, giving presentations, and taking lessons learned and really implementing those. It's a lot of work, and these students are volunteering their time, so that's been huge. So with that, I believe we have a good amount of time for some questions, Katie. If I'm not able to answer your question today, my email address is on there, on the screen, so definitely do send me an email, and I will be sure to address that as quickly as I can. So yeah, Katie, do you have any questions?
We do actually have several questions. The first one is from Joel, and he's asking, what view in core did you use to generate the diagram that you have on slide 11? And I didn't get a chance to look back for that, so if you could share a little bit more with us on that one.
Yeah, so this would be the requirement diagram. So if I understand the question correctly, Joel, it looks like you're wondering what type of diagram this was and how we got to it. And so within within a requirement class or a requirement element, the icon itself looks a little bit similar to the traceability diagrams, but this would be a requirements diagram. And so so it takes the traceability diagram, but just adds a description to it as well. In terms of the actual location of the button, I'm not quite sure, but it's I believe on the right-hand side, underneath the traceability aspect.
All right, great, thank you. We've got one from Alice, and she asks if you could give an example of one systems engineering concept that really didn't hit home until you started working through the modeling process in core.
That's a really good question. Yeah, I think one of the reasons I like working with core so much is because it's able to capture very complex interrelationships. And that really wasn't something that I fully understood when I was learning the process of systems engineering and the methodologies therewith. But there's a lot of details to capture, and not only a lot of details, but a lot of it's the organization of those details and how they impact each other that's been very, very fun to work on, but also definitely a challenge in the amount of forethought it takes to consider that, to consider how this puzzle really fits together. But core is very good at managing those details and breaking things apart and looking at the traceability and looking at the impact of one design element on another. So that would probably be my I think that'd be the largest area that was a little bit of a surprise to me, but it's been definitely a joy to see.
Okay, thank you. And then we've got another question. Were you able to use core for tracking the progress of the verification of your requirements?
Yeah, so ultimately, we would like to. At the moment, we're still kind of getting started on that path of implementing the verification requirement elements within core, and then developing the testing procedures to meet those. So testing has started in some areas, but we do need to fill out the verification class a little bit more so that we could keep track ultimately of which ones have been met and which ones remain to be addressed.
Okay, and this is kind of a long question here, but is core the main tool used by your team members to regularly access requirements, SDDs, and other information, or do they reference documents that are outputs from core? So in other words, is everyone on your team using core regularly, or is it just the systems engineer?
Yeah, so it's primarily the systems engineers that have access to core and really understand the program and how to run it and all the elements that are within core. The system description documents are output, and that's really the team's primary interface with the requirements. Occasionally, they'll refer to the originating requirement documents, but for the most part, it is the system description documents and the requirement matrix, the 9-page table of index, basically, that subsystems use in order to make sure that they're addressing all the requirements that pertain to their system and making sure that they understand all the details and all that is expected of their system.
Okay, thank you. And then another one, how did core help you respond to changes in the systems requirements over time? I know you mentioned there's been several stages of changes there.
Yeah, that's another good question. Yeah, so, as I mentioned with that ARL diagram for the band plan, looking at the flow down of requirements that originated from that document. That's been a huge help in identifying what needs to be updated given a document change. And so, for example, like with the revision statement to the NanoRacks requirement documents, within there they revise some of the testing procedures, or testing specifications, I guess, and also their overall mass requirement for the satellite, which was a big one. But we were immediately able to see exactly what was impacted because we had that aspect of traceability developed. So we were able to go into the, the children requirements, I guess, of the NanoRacks requirement document, and identify which ones within that list of child requirements were impacted by those revision statements, and revise those accordingly, and then go ahead and add the revision statement to the document class so that it continues to grow and it is also actively updated and whatnot.
Okay, thank you very much. All right, so I have another question asking about how long does it take to orient a new student to core and the SE process when you guys are adding someone to the project?
Yeah, it's an ongoing process for sure, and so this is the first time I've had the opportunity to mentor someone else. I know when Dr. Ye was working with me initially, it took several weeks, I guess, to get caught up to speed on how to use core, and then, within the coming months, I'd come back with questions, or, as I expanded my knowledge there. But I really don't have the experience to really say how long it takes for a student to mentor another student. That's a new process, but I would imagine it would definitely take a couple weeks to not only get up, not only learn the program, but also get introduced to the project itself. The requirements that are associated with the risks, and some of the challenges, and really how things operate, I guess. So yeah, hopefully that answered the question.
Okay, great. Yeah, and hopefully that did. And if not, hopefully the individual asking the question can reach back out and let me know. And let's see. So I believe we have time for one more here, and there are several others, so we will get those over to Marcus. So the last one here is, how have you integrated COTS boards in your core model? So for example, these boards belong to the physical architecture and imply no requirements, but ICDs.
Yeah, let's see. Could you repeat what boards those were?
The COTS, and I'm sorry, I'm not a technical expert, so I'm not familiar
You know, I was
Commercial off the shelf.
Oh, it says boards that you buy already designed and developed. We did get a clarification. So commercial off the shelf, that's what he's referring to.
Okay, thank you. Sorry, with that, could you repeat the question one more time?
Okay, so how did you integrate the commercial boards, so boards that you've just purchased, into your core model? So and it says, for example, the boards belong to the physical architecture, but they don't imply any new requirements.
Yeah, okay. I understand the question now, so thank you for clarifying that. Yeah, so I guess when we bought the onboard computer, you know, it came with its own specifications, and we were able to choose, we were able to configure it as we wanted before we actually purchased the hardware, such that it would interface with our existing architecture. And so that really made the job a lot easier, in that we didn't have to spend too much time looking at these specifications and work our satellite around that. Rather, you know, Pumpkin had a variety of options that we could choose from. In terms of software, there have been, I know there's some challenges in using a lot of the existing architecture that Pumpkin has given us with that onboard computer. So that's just, you know, it's required a lot of work then on the part of the subsystem team leads and the team members in order to really understand how that purchased platform operates, and then design the software that'll fit that to fit that platform. But you know, at the moment, we haven't gone that detailed within the core database, and so within core, we haven't captured the that process that they've been undertaking specific to that.
All right, and I know that that's one of the nice parts of the layered-based approach, is that you can gradually go down into that detail as you come across it. And let's see, so that is all the time that we have for questions today. I really appreciate everyone's questions. If you have any additional questions that we didn't get to, we will get those over to Marcus, or if you have any that come up, please, as he said, feel free to go ahead and contact him, or you can actually go on to Vitech's group page on LinkedIn. If you just go to linkedin.com and then search for Vitech Corporation, you'll find a group page. You can ask questions there, and we will make sure that either Marcus or one of our systems engineers gets a chance to see and respond to your question. And let's see, and I do know that we had some technical difficulties today. Just so that everybody knows, we're going to go ahead and try and edit those out for the recording. So if you want to share that recording with anybody, we'll be able to hopefully try and correct that for you so that the recording is seamless. And thank you so much for attending today's webinar. Please keep an eye on your inbox for our next webinar invitations coming in the next few weeks. You can also stay up to date on our upcoming webinars by visiting our webinar calendar on the Services and Training area of our website at www.vitechcorp.com. And just one more note, at the conclusion of this webinar, a survey should open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Once again, thank you so much and have a wonderful day.